Hello, my name is Dr. Jacob Hudis, and welcome to my new playlist, Mastering Quantum Mechanics Through Problems.
This is a dream come
Today
true.
I have a fantastic problem to go over with you about simultaneously diagonalizable matrices. It's under the umbrella of Mathematical Foundations of Quantum Mechanics. I hope you'll learn a lot and have fun while we go over this problem. You might ask, can learning and fun be simultaneously diagonalizable? If I'm teaching, I think they can be. To begin, let's read the problem.
I'm so stoked.
When two matrices commute, they share a common set of eigenvectors. In this problem, we will verify this by considering the following two 3x3 symmetric matrices. Here's matrix M. As you can see, it's symmetric. Here's matrix T. It's a 3x3 matrix. And as you can see, this is symmetric. By the way, both of these matrices are real. And so any real symmetric matrix is also Hermitian. And in quantum mechanics, we're interested in Hermitian and unitary matrices. And unitary matrices are the exponential map of Hermitian matrices. Part A. Show that the commutator of M and T vanishes. That is, the commutator M comma T is defined to be MT minus TM and show that this is equal to 0. Part B. Determine the eigenvalues of both M and T. Part C. Identify the eigenvectors of T and show that they are also eigenvectors of M. Part D. Find the eigenvectors of M and confirm that they are also eigenvectors of T. This is an exciting problem, so buckle up. It's going to be a wild ride. Now let's do Part A. So Part A asks us to calculate the commutator of the matrices M and T. That's M times T minus T times M. This is matrix M multiplied by matrix T minus matrix T multiplied by matrix M. Matrix M times matrix T is equal to this matrix. Matrix T times matrix M is equal to this matrix. And as you notice, these matrices are the same. Therefore, the commutator is equal to 0. It's equal to a 3x3 matrix with zeros everywhere. And now let's look at the implications of what it means for the commutator to equal to 0.
Terrific!
Part B says determine the eigenvalues of both M and T. This is matrix M. This is matrix T. This is the procedure to do that. The eigenvalue equation is M onto ket omega I equals eigenvalue omega I onto ket omega I. This is the matrix M. This is a vector. It's in the ket symbol. This is a constant called the eigenvalue, and this is a vector, which is the ket. An eigenvalue equation tells you that if you multiply the matrix by a specific vector called the eigenvector, you'll get a constant times that vector back, and we want to find the specific vectors and these constants. This is called the eigenvector and the eigenvalue. This is the eigenvector equation. I can subtract the right side over and rewrite the eigenvalue equation like this. To find the eigenvalues omega I, we solve the characteristic equation, which is the determinant of the matrix M minus omega times the identity matrix, and this has to equal to 0. A matrix is singular when its determinant is 0. For the eigenvector equation, M onto ket omega I equals eigenvalue omega I onto ket omega I. To have non-trivial solutions, this matrix must be singular. So for example, I could always choose the ket equal to all zeros, but that's trivial and that's not useful and we don't care about that. Solving this equation is how we get the eigenvalues. And then once we have the eigenvalues, we just plug them back in to get the eigenvectors. This is very standard stuff in quantum mechanics that you need to know how to do. If you have any more insight on why taking the determinant of this equals 0 is how we solve the eigenvalues, please let us know in the comments section below. On the next slide, let's go through this all and do it in detail.
Shut the front door.
I want to start by finding the eigenvalues of the matrix M. In order to do that, the procedure is always to take the determinant of the matrix M minus omega times the identity matrix. This is how you always do it. The identity matrix has 1s down the diagonals, and so ultimately what you do is you take the determinant of the matrix M minus omega down the diagonals. This is M, and I would take minus omega, minus omega, minus omega. You see there's 0 here, that's why it's just minus omega, 1 minus omega, and 1 minus omega. Then you take the determinant of this. The determinant would be this number multiplied by this times this, minus 0, so you don't do anything for that, plus this number, which is 1, multiplied by 0, 0, minus, which is plus omega times 1. And so this is what we call the characteristic equation. And you can factor out a 1 minus omega and do a little bit of algebra. And then the characteristic equation looks like this. And then the characteristic equation looks like this. Now you set the characteristic equation equal to 0, and that tells us that omega squared is equal to 0, as well as 2 minus omega is equal to 0, and there are 3 eigenvalues of the matrix M. Omega 1 is 0, omega 2 is 0, omega 3 is 2. This has a degeneracy, and that's fine. Now let's do the same thing for matrix T. So we take matrix T minus lambda. I'm going to call the eigenvalues of M omega and the eigenvalues of T lambda just to reduce confusion. We can't call them both omega or it would be too confusing. I'm going to take the determinant of T minus lambda I, where lambda are the eigenvalues of the matrix T, and take the determinant of this, set it equal to 0, and get a characteristic equation. And so we'll take 2 minus lambda times this, minus this, minus 1 times this, plus 0. And this is our characteristic equation. And now we want to solve this equation for lambda. We'll set this equal to 0. So one of the lambdas is equal to 2. And then you'll set this equal to 0. And you can use the quadratic formula. And then you'll get your other lambdas are equal to 1 minus root 3 and 1 plus root 3. And so now we have the eigenvalues for both matrix T and matrix M. These are the eigenvalues for matrix M. And these are the eigenvalues for matrix T. There are 3 eigenvalues for matrix T, and there are 3 eigenvalues for matrix M, and there's going to be 3 eigenvectors for matrix T and 3 eigenvectors for matrix M. Now let's take a look at part C. So part C says identify the eigenvectors of T and show that they are also eigenvectors of M. So let's first find the eigenvectors of the matrix T. To find the eigenvectors of the matrix T, I take the matrix T minus lambda times the identity matrix, and that has to equal to 0. Let's begin with lambda equal to 2. This was one of the eigenvalues. When lambda is equal to 2, I subtract 2 down the diagonal for matrix T, so you'll have 0, minus 2, 0, and that's this matrix. And if I multiply by x, y, and z, that has to equal to 0. The first row times the column tells us that y is equal to 0. It's 0x plus y plus 0e plus 0z is equal to 0. Therefore, y is equal to 0. And then, if I take this row times this column, that tells that x minus 2y minus z is equal to 0, but we know that y is equal to 0, so therefore x minus z is equal to 0 and x is equal to z. If I choose x equal to 1, then z is 1 and y is 0, so this is an eigenvector corresponding to lambda equal to 2. Now we do the same procedure for the other 2 lambdas. For lambda 2 equals 1 minus root 3, I'll subtract that down the diagonal, so 2 minus 1 minus root 3 is 1 plus root 3. 0 minus 1 minus root 3 is minus 1 plus root 3. And then again, we have 1 plus root 3. And it's the same procedure. You take this matrix, you multiply by the vector x, y, and z, you set it equal to 0. The first equation tells us that 1 plus root 3 times x plus 1 times y is equal to 0, which says that y is equal to minus 1 plus root 3x. And then the third equation tells us that minus y plus 1 plus root 3z is equal to 0, which says y is equal to 1 plus root 3z. If I choose x is equal to minus 1, then y is equal to 1 plus root 3, and if y is equal to 1 plus root 3, z must equal to plus 1, and therefore this is the eigenvector corresponding to the eigenvalue 1 minus root 3. The final eigenvector you get the same exact way. You can look at the work here. It's absolutely the same sort of procedure. The eigenvector corresponding to the eigenvalue 1 plus root 3 is this vector, minus 1, 1 minus root 3, and 1. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis. Part C says identify the eigenvectors of T and show that they are also eigenvectors of M. So these are the 3 eigenvectors of matrix T that we just found. For the eigenvalue lambda equals to 2, the eigenvector is 1, 0, 1. For the eigenvalue lambda 2 is equal to 1 minus root 3, the eigenvector is here. And for the eigenvalue 1 plus root 3, the eigenvector is minus 1, 1 minus root 3, and 1. Now what we want to do is show that these are also eigenvectors of the matrix M, because the point is M and T both commute. They're simultaneously diagonalizable. M onto lambda 1, this is the matrix M, and if we multiply it onto lambda 1, that's equal to 2, 0, 2, which is equal to 2 times lambda 1. It is an eigenvector.
Amazing.
M onto lambda 2, this is the matrix M, this is lambda 2, the eigenvector lambda 2, and this is equal to 0 times the eigenvector lambda 2, and then M onto lambda 3 is equal to 0 times the eigenvector lambda 3, and as you can see, the eigenvectors of T are also eigenvectors of M. Now let's look at part D. Find the eigenvectors of M and confirm that they are also eigenvectors of T. This is the matrix M. M had 2 degenerate eigenvalues equal to 0. So if I subtract 0 down the diagonal, it doesn't change anything. I still have M. So if I take the matrix M and I multiply it by the vector x, y, z and set it equal to 0, that tells that x plus z is equal to 0. That tells me that y is unconstrained. Y can be anything that I want it to be. and those are the equations that I have. So I know that x is equal to negative z, and I'm going to just choose y to be 0 because y can be anything I want it to be. And so one of the eigenvectors corresponding to omega 1 is equal to 0 is 1, 0, minus 1. Now because y can be anything I want it to be, another eigenvector that I can choose corresponding to the other eigenvalue of the same degenerate eigenvalue omega 2 equal to 0 can be 0, 1, 0. And if this is confusing, I recommend that you take this matrix and you multiply by this vector, and then you get 0, and that shows that this is an eigenvalue equation because this is not a non-zero vector. And if you take this matrix and you multiply by this vector, you also get 0, which shows that this is an eigenvector of the matrix with eigenvalue equal to 0. The third eigenvalue was omega 3 is equal to 2. This is the eigenvector corresponding to the eigenvalue of 2 for the matrix M. Now what I want to show is that these eigenvectors are also eigenvectors of matrix T. So I'm going to take T, for example, and multiply it by this eigenvector 1, 0, 1, and T onto the eigenvector omega 3 is equal to 202, which is 2 times this eigenvector. As you can see, this eigenvector of M is also an eigenvector of T. Now let's try it for the other two eigenvectors. This is the matrix T. I'm going to multiply it by the eigenvector for matrix M, and this is the matrix T, and I'm going to multiply it by the eigenvector for matrix M, and as you can see, oh, this is a little awkward. These actually aren't eigenvectors. So the eigenvector of M is not actually an eigenvector of T. This is quite uncomfortable. What's going on here? Can you explain it? I think I have an idea. I can show you on the next slide, but maybe you know the answer. So remember that we said if T and M commute, they share a common set of eigenvectors. Because there are two eigenvectors of M with the same eigenvalue, 0 in this case, any linear combination of omega 1 and omega 2 is also an eigenvector of M. So I can take linear combinations of these eigenvectors to get this eigenvector. So in order to simultaneously diagonalize the matrices, these are the eigenvectors. These eigenvectors are eigenvectors of both matrices. Alpha 1 is the eigenvector 1, minus 1, 1 plus root 3, 1. Alpha 2 is the eigenvector minus 1, 1 minus root 3, 1. And alpha 3 is the eigenvector 1, 0, 1. And these eigenvectors are eigenvectors of both M and T. If M and T commute, it's possible to find eigenvectors that are eigenvectors of both matrices. If they don't commute, do you think that's possible? And of course the answer is no. That's what it means for the commutator to equal to 0. If the commutator equals to 0, then you can find eigenvectors that are eigenvectors of both of the matrices. That's what it means for the commutator to equal to 0. If the commutator equal to 0, then you can find eigenvectors that are eigenvectors of both matrices. If the commutator is not equal to 0, then the matrices are not simultaneously diagonalizable, and you will never be able to find that. If you have questions, or if you want me to clarify things, or if you want to add information or add your own ideas, please leave comments in the comment section below. Also, like and subscribe to my channel, as I'm going to be putting up a lot more quantum mechanics problems and solutions in the near future.
Shut the front door. I'm loving this physics lesson. Please tell me much more. I can't wait to tell my friends and family what I am learning about. Woo-hoo.